Today I'm going to tell you about a project that I've been working on for about the last decade. It's called HEG Neurofeedback. It's a device that I've been working on. It looks like this, and it can read your brain activity. So the short version is that the way we do this is that we measure brain activity using light. It's very similar to a pulse oximeter. And with that information, we can give you feedback in real time, and we can teach you how to increase your brain activity consciously. And that serves as a brain exercise, which may be useful for things like improving people's focus and attention, or improving people's ability to integrate stimuli, and might also help with recovery from traumatic brain injuries or reducing migraines. And it also might just make you better able to think in general. So it has a lot of promise. It also has a lot of advantages over existing technologies that you may have heard of, like EEG, and I'll be going over some of those in the future. So it's a very exciting thing. So again, I said that it works by measuring the optical properties of your tissue. And you might not know this, but human tissue is actually very translucent to light. It allows light to go through your body pretty well. It refracts it around, it bends it around, and it absorbs the shorter wavelength colors like green and blue, but red and infrared pass through your body pretty well, as you can see by this picture. And you can see like a lot of the light is coming up through her orbits, and you can even see some coming through her cheekbones. So bone is not actually an obstacle to this. Bone is white, so it doesn't actually absorb light. The main thing that absorbs light in the human body is the skin, the hair, and blood and muscle. If we have multiple wavelengths of light, we can find out some really interesting stuff about what's going on in the body. Specifically, blood changes color based on the oxygenation. So if you use 2 wavelengths of light and you measure, for example, right here where oxygenated blood absorbs the least light, and over here where it absorbs about the same amount, you can infer the oxygenation of the blood just by measuring those 2 wavelengths, basically by measuring the color in the red infrared region. And if we put a couple of LEDs and a photodetector on your head, we can send light through your skull into the top layers of the brain, into the neocortex, and then some of it will come back out where the photodetector is, and that allows us to measure the oxygenation of the blood in your brain. When we do this, we get 2 components to the signal. One component is just this kind of waveform, which this is about 5 seconds, 10 seconds. So each one of these spikes is a heartbeat. So you can see your heartbeat very clearly. We also get a longer-term oscillation, which is called the Meyer wave. This is a breathing-related waveform, but it's actually not breathing itself that's causing the change. It's actually the pumping action of your lungs and the autonomic nervous system acting to redirect air from your lungs to your brain when you're exhaling, and then back to your lungs when you're inhaling, so that you maximize the efficiency of your lungs. So this technology, when you're just doing a single wavelength, it's called photoplethysmography. It's basically the optical measurement of volume. But what we do is we go farther than that. We're actually measuring the oxygenation. So, and this field has been studied pretty well. We've seen that when a person engages in a burst of mental activity or neural activity for, say, 2 seconds, you see an increase in blood flow afterwards that lasts for about 10 seconds, and that comes with a ton of fresh oxygenated blood to that area. There's also a small decrease in deoxygenated blood because that fresh oxygenated blood displaces the old used blood. So this is a little bit counterintuitive, but what's happening is that the demand for blood or the demand for energy causes an increase in blood flow that more than compensates for the used oxygen. So you actually see an increase in oxygenation when oxygen is used. Counterintuitive, but it's a very well-established finding. And this is, by the way, the basis behind fMRI, which is the most commonly used imaging technique in neuroscience nowadays. So there is also a contribution from the skin and the skull. The skin does have variations in blood flow. Like if you've ever seen somebody blush, you know that. The skin is a confound. It's not actually like an overwhelming confound. If you are looking at a functional event-related signal, the skin doesn't usually change that much, but the brain signal does. In any case, if you have multiple distances, you can usually subtract out that signal because the skin is going to have the same contribution to the short distance as to the long distance. So if you take long distance minus short distance, you remove the common signal and you just have the different signal, which is the extra brain tissue. So people have compared this measurement technology against fMRI, and they've done this, for example, with finger tapping experiments. So if you tap your right finger, then a little spot on your left motor cortex lights up. If you tap your left finger, right lights up. So they've done this with fMRI many, many times. People have also done the same thing with functional near-infrared spectroscopy, and you get the same result. So why do we want to use fMRI or near-infrared spectroscopy instead of EEG? After all, the brain is electrical. Doesn't it make sense to measure electrical activity? And it sort of does, and that's what people thought for a long time, but it turns out that there's a lot of problems with EEG. And anybody who's worked with EEG knows this. You get a really noisy signal. It's always either messy or like really noisy or both. You get a lot of interference from like electrical activity in nearby instruments or just from the muscles. Your eye muscles will produce a much larger signal than your brain ever will. You get a signal of about 100 microvolts from an eye blink, and you get about 100 millivolts from an eye blink, 20 microvolts from the brain. So anytime there's any kind of muscle activity in the eyes, you just completely lose all EEG, and you have to manually filter it out. It's a big pain to do that. But that's not even the worst of it. There's also problems just with what EEG measures. When you're measuring at the scalp, you actually lose most of the information from the individual neurons, and you don't get to see when neurons are active. You only get to see when neurons are active in large groups at exactly the same time. And if they are processing information, they're usually going to be firing just out of phase with each other, and then those signals will interfere with each other, and you won't see it at the scalp. So it's only when they're firing in phase with each other, in the same direction, that it makes it to the scalp. And that's actually a fairly rare scenario for information processing. Usually what it indicates is either when different parts of your brain are just idling and they're like engaging in this rhythm of idle activity where they're just sending the same information back and forth, or if you get a large burst of information coming in from a distant region all at once. So yeah, and this just kind of shows you that there's, you have to have the neurons arranged in order, in like a row, in parallel, in order for any signal to show up at the EEG. And most of the neurons aren't arranged this way. It's only a very small subset of neurons that have that arrangement. So you get to only see a very small subset of the total activity with EEG. And if you instead look at HEG, or functional near-infrared spectroscopy, you get a measure of total activation. You get a measure of total energy usage, which is a much easier signal to interpret. It's also a lot less prone to those muscle artifacts. There is still some artifacts. If, for example, you blink your eyes, that's not going to change the signal unless you blink with your eyebrows. And that changes the signal because it moves the device relative to your brain. And there's not much we can do about that except detect it and clean it out. But it happens a lot less often, and you can also train the subjects to just not do that. The spatial resolution is a little bit better than EEG. Temporal resolution is nowhere near as good as EEG. You can get like 10 millisecond or better resolution with EEG, and with functional near-infrared spectroscopy, you're limited to the rate at which blood flow changes, which is on the order of a few seconds. But it's still not that bad, and it's still similar to the order, or to the time span for which people actually think. So it's similar to conscious experience, so it's not too hard for people to get a handle for it. Another big advantage for this technology is that the spot that it works best on is your forehead, or the prefrontal cortex, and that's also the spot that EEG works worst on. Skipping ahead, the prefrontal cortex is the part of the brain that has been changing the most in recent human evolutionary history. So it comprises something like 28% of the human brain and something like 7% of the dog brain. And whenever something grows that much over the time span of a few million years, you get bugs. You get issues with certain things not always working completely properly. And so a lot of the disorders that we see in humans, psychiatric disorders, are actually prefrontal dysfunction disorders. Also just a lot of the issues that we have, like dealing with school, having that executive function to sit down and do your homework every night, that's a prefrontal thing. So if we were able to improve prefrontal function, it could help us a lot, and EEG just can't do that very well because it has the worst signal-to-noise ratio in that area. So the killer app for functional near-infrared spectroscopy, in my opinion, is biofeedback. So again, biofeedback is where you measure something about a person's body and give them real-time feedback and use that feedback to teach them how to change that part of their body. So with biofeedback, you can do some really interesting things, like you can teach people how to make their fingers warmer, or you can teach them how to make their fingers colder. You can teach them how to make their hands sweat or to make their hands drier. As long as you can measure it and as long as it's in some way, preferably directly, but sometimes also indirectly controlled by the nervous system, you can learn how to control that part of your body. And you can also do this with your brain activity, and when you do that, it's called neurofeedback. So biofeedback is a superset, neurofeedback is a subset of biofeedback. And people have done this with fMRI. They've done some studies in which they modulated the amygdala activity, and with that modulation, they were able to change how much fear people retained after making some association between some stimulus and a fearful response. So when they downregulated the amygdala activity, they saw lower activation, lower reported fear. This is actually pain rating. This is a different study from this one. My apologies. But yeah, they also did a similar thing with anterior cingulate activity and pain. If you downregulate the anterior cingulate, you can reduce the amount of pain that people experience. So several different studies have done this where they change activation of a part of the brain and look for effects on cognition. And with fMRI, that's been shown a few times to have an effect. Unfortunately, fMRI is ridiculously expensive, so this is not viable except in a laboratory setting. Like each session costs like $500 just for the time with a magnet. And that makes it unviable, but with functional near-infrared spectroscopy, you can get the entire instrument for less than that, and you can do as many sessions as you want. So the term HEG was coined by my grandfather. He used it to refer to the neurofeedback application, but literally it just means measuring blood in the brain. But yeah, it's usually used to refer specifically to measuring and doing biofeedback with it. And we've seen that people are often very quickly able to gain control over that. This is a session that I did with a person on his first time. He had no prior experience, and we did a 10-minute training session. And over that time period, he was able to increase his activation by about 30%. And we see this square root of x kind of shaped curve. The increasing your activation gets harder the more activation you have. There's kind of a ceiling or a soft ceiling. So as time went on, he kept trying, but he kept making less progress. But he kept having to try continuously at full effort in order to stay where he was. And then as soon as we finished, and he started talking, his brain activation shot down. Then I started talking for a while, and his activation stayed constant. And then his activation shot down again when he started talking again. And we did this several times. We did another 5-minute training session, then he started talking. And this subject was very interesting because he had attention deficit disorder. And one of the endophenotypes of attention deficit disorder is reduced prefrontal activation whenever they engage in a task. Whereas with most people, you see increased prefrontal activation whenever they engage in a task. And so that showed up really clearly on his results. As soon as he started talking, he shut down his prefrontal cortex, and his mind would wander around. I've done a lot of other studies in which we've tested that hypothesis of whether people can consciously control it. For example, have removed feedback and had people try to maintain that state. And it usually does work. Once you learn how to do it, you can do it without the feedback, but the feedback tends to make people better able to do it, gives them better conscious control, and also gives them reward. It makes it so that the entire activity is fun. And here's another one of those experiments. In this case, we had a 5-minute resting period at the beginning and at the end. This particular subject got startled when I walked in the middle, so that was actually her freezing and then blushing. So those kinds of things do happen, and you can also see a motion artifact. So on the top we have the HEG signal, the near-infrared spectroscopy oxygenation signal. On the bottom we have EEG signal, specifically beta activity over, I believe this was P4 and C4. And we saw a really interesting increase that was almost immediate in those beta frequencies that increased over time and got really, really huge. And those increases also correlated with the oxygenation. Now this is unusual because this was also her first time, And usually when you do EEG neurofeedback, it takes 5 or 10 sessions before people get control over it, and they very rarely are able to produce nearly 3-fold increases in beta frequencies. That's very surprising. This person was able to do it on her first try, and she wasn't even the only one to do that. On the other hand, I also did the inverse experiment where I had people, instead of trying to increase this signal, I had them increase this gray signal that you can only barely see. And this subject took about 5 sessions before he was able to do it. And when he did that, he only increased the signal at the one electrode that he was training, and there was no effect on the oxygenation. So this seems to demonstrate that there is a one-way relationship. When you change oxygenation and when you change overall activation as measured with this device, it also changes electrical activity. But when you change electrical activity, it only changes electrical activity in specifically the way that you're measuring. So that is both good and bad. This means that this is more of a general kind of thing. It's a one-size-fits-all kind of thing. And also, like, the effects are global. So as long as the effect is good, then that means that there's not that much tweaking to be done. But if you want to tweak, then EEG can actually be better. More of the same. Oh, actually, this does show that when you do training on one location and passively measure on another location, you see increases in both locations. So it is a regional increase in blood oxygenation, which is a little bit surprising from the neuroscientific view, but it is what it is. That's what the data show. Does anybody want to actually try it? And so the way the system works is that forward motion indicates an increase in activation, and backward motion indicates a decrease. So your goal is to go forward as far as you can. It will go backward on occasion. When that happens, try not to get frustrated. Just take that as a reminder to renew your focus and renew your concentration. And your goal is to get as far forward as you can. If you make it to about like 3 or 4%, the scene will switch, so don't be disturbed by that, just keep going. And about 50% of people are able to do this on their first try. And usually when people get it, it's like within 1 or 2 minutes. It's really surprising. This suggests to me that what people are doing when they're doing this therapy is something that a lot of people already know how to do. It's something that they've instinctively learned as a way that they can improve their own concentration. And what this device does for those people is it teaches them how to use that to a much greater extent than they normally would. It makes it so that they can do it consciously instead of subconsciously. And instead of going maybe 5 or 10% above, they can often make it to 30% increase in activation. And that's for about half of people. That's for the people who get it intuitively. For the other half of people, they don't know how to do this. And it usually takes several hours of training for those people before it finally clicks for them. And for them, it's actually a learning experience. It's where they can figure out some new mechanism for improving their concentration that they didn't have. That latter category, though, is a lot harder to keep motivated because you have to keep them going through that 3 to 4 hour or 3 to 5 hour training period. So yeah, this is an example of somebody who got it immediately. Could you tell that?
Oh, no, I messed it up. You guys got me on concentration.
This might actually be a motion artifact. Not entirely sure, but yeah, if it's a motion artifact, so it's coming right back. So that is actually probably because he was laughing and moving the device. So it's going close back to his original level. But yeah, you can see that pretty consistent upward trend. And that's what people usually show when they get control over it. It's a long-term trend with diminished variability and like a positive bias. When people don't have control, there's usually a higher proportion of total variability that's like random and chaotic, and you don't see that long-term trend. And also people tend to show frustration. Yeah, I'm going to stop you here. So yeah, you were able to increase your brain blood oxygenation metric by 8.7% in 2.4 minutes.
Wow. Thank you. Painless.
Yeah. Subjectively, I found that a lot of the time when I experience brain fog, if I put this on and do a session, it just makes the brain fog evaporate. Like I've had some times when I've been trying over and over again to like concentrate and do some work, and I spend like an hour and I make very little progress, and I think maybe I'm hungry and maybe I need some food, so I go out and eat, and then come back and I spend another hour trying to work and nothing happens. and then I do 15 minutes of this, and then the next half hour I can get twice as much done as I got done in the previous 2 hours. It doesn't work every time, but it does seem to work a lot of the time for me. Other people report different subjective acute effects. Some people report that they get fatigued after this. So you do have to be a little bit cautious. If people get fatigued, they usually feel stronger or better a few days later. It's kind of like when you go to the gym, your muscles get sore, but they get stronger in the long term. Did you have a question?
When you do a session, how long do you do it for?
Depends on my mood. So with newbies, I try to keep it down to 3 minutes to avoid that overtraining effect. And with more experience, even if they do have like that fatigue initially, they're usually able to go longer after the second or third session. Typically what we do after people have gotten initiated and gotten used to it is we do three sessions of 10 minutes each per day. So a person might sit down, do 10 minutes on like the left prefrontal cortex, then rest for 5 or 10 minutes, then do another 10 minutes on the right prefrontal cortex, rest for 5 or 10, then do another 10 minutes on the center. And that seems to be a pretty popular protocol. You can also do longer, but that's less common. I like to do sometimes 20, 30-minute sessions just to see how far in I can get dialed in on whatever part of the brain that I'm measuring from. So that's kind of how it works. And when we've had people do this on a regular basis, do like 10, 20, 40 sessions, we do see chronic changes in oxygenation and blood flow. So this is a SPECT. This is a type of neuroimaging study that measures blood flow at like baseline. It's done over, I think, 40 minutes, where they inject you with a radioactive tracer, and then they see how much of that tracer gets emitted in which parts. And blue and purple is below normal activation. Red is above normal activation. The green is also below normal. And so in this case, we saw a lot of the anterior temporal pole. This is like right here. This is the right side of the brain and sort of towards the front. This is the forehead. So this part here is the temporal lobe. And most of that hypoactivation was completely resolved by the time of the retest. And I think we've done others. This one is, I believe, several different people averaged together. And you see a prominent increase in activation in the center, the medial prefrontal cortical area, which is around where we do the training most of the time. And again, you also see an increase in activation in the temporal lobes, which is actually quite pronounced. That doesn't mean that it helps, but it is certainly interesting. Also, keep in mind that, unfortunately, none of these studies had proper control groups. So it could just be that when you do something to people, they magically make their brains more blood flowy and better and happier. I don't know. My grandfather also did some studies in which he did microcog analysis before and after, which is basically a computerized IQ test. And people improve over time, and the amount of improvement is proportional to the number of sessions that they do. So that's a good sign, but again, no control group. So one of the more common patient types, or the group types that like to do this training, is people with attention problems. And one of the more common tests for measuring attention is a continuous performance test, where you have boxes that either appear at the bottom of the screen or on the top of the screen, and you have to press a button when the box appears at the bottom, but not at the top. And people will often make the mistake of failing to press the button when something appears at the bottom, or pressing the button when it's at the top because they saw a bunch of boxes in the bottom in a row. And people with ADHD tend to perform a lot worse on this test than people without it. And in this case, there was actually a control group. It's not a perfect control group, but a control group that did 1/3 as much training. And so the group that did the full 30 minutes of training improved about 3 times as much as the group that only did 10 minutes of training. So that indicates a dose proportional response, which is a good sign, but not quite proof, because they probably still knew that they were only getting 10 minutes of training, and that might have made them only try 33% as hard. It also has been compared to EEG neurofeedback for improving attention in ADHD, and the HEG studies tend to show much higher effects per session, so it seems to be much more efficient in terms of the time use. And I guess before I finish, there's also been some interesting stuff done with autism. There was a study done in Thailand in the 90s. Thailand's got autism in the royal family, so they tend to fund a lot of autism research, and they've got specifically a school up there that's associated with the hospital, and so they have very severely autistic kids that are actually in school. And when they did 40 sessions of training on some of these kids, their grade point averages improved by about 1 grade point, like the difference between a C and a B, basically. We also got some really interesting data on the activation. We noticed that their baseline activation levels, as measured by this device, increased by about 20%, and the range, the dynamic range, increased by about 50%. But again, no control group. So one of the things that I hope to do is to refine the software to make it possible to do double-blind sham treatment controls, or to do controls where people have no idea whether they're getting positive feedback or negative feedback, and to see what kind of effects those have. But that's work for the future. I'm also working on improving the hardware and trying to make it so that it's mass producible and cheap. So hopefully in a few months that'll be out. Questions?
Yeah. Are you familiar with the Muse device?
Yep.
It seems like that's almost opposite to what you're doing, and that they're trying to help meditate and relax your brain.
Yeah. So that's an EEG device. It's one of the many EEG devices. It's also one of the better made of the recent crop of consumer EEG devices. It still does have significant signal-to-noise ratio issues. Specifically, it's got like a lot of problems where if you don't get it seated just right, two of the electrodes, especially the front electrodes, don't make good contact. And all of the electrodes are very close to the eyes, so you just get a lot of eye movement and eye blink noise in there. But given what they have as their basic measure, they have to make the best of it. And I mentioned that the EEG is measuring when neurons are active synchronously, and a lot of that is idle rhythms. And a lot of meditation is about shutting down your brain, which means allowing those idle rhythms to become more prominent. So that's mostly what the EEG devices have as their low-hanging fruit. And what we have as our low-hanging fruit is increasing activation. I have my own biases about which one's better, obviously.
It would be interesting to try to test which one's better.
Yeah. It would be interesting to try to test which one's better. Not specific things. But yeah, so...
Well, no, I don't mean in terms of the modality as much as in terms of what you're trying to, what the end effect of going through your game versus their game is.
Right. So for example, if you had a bunch of people with ADHD and you were measuring how quickly they improved under either HEG training or EEG training, you might end up with a graph that looks like this. Yeah. But it is kind of interesting. I found that experienced meditators are usually less able to do this than like random kids. Also, neuroscientists, surprisingly, are a little bit worse than average at doing this.
Would you be able to use this technique to test whether nootropics are effective or not?
I wish. Unfortunately, in order to make sense of the signal, we have to do some sort of subtraction. Usually, there is a small component to the signal that is not proportional on, or not dependent on exactly where you place it on the head, but mostly you have to put the device on, take some baseline measurement, and then measure all subsequent time samples relative to that. And you could do something where you, for example, put the device on, started doing measurement, took that baseline, made sure that they were very still, and then gave them vinpocetine or something, and measured their brain activation or brain oxygenation change over time. But you'd have to be very careful about the logistics, and it wouldn't really tell you that much. Like, if you take caffeine, it will tell you that your brain activation decreases. But wait, isn't caffeine supposed to increase your brain activation? Well, no, in this particular case, it's because caffeine is a vasoconstrictive agent. It constricts blood vessels, but it makes neurons more active. So caffeine actually breaks that relationship between between blood oxygenation and activation. So yeah, interpretation is difficult, and also measurement is difficult with that.
Have you ever done this with like a VR device?
I have not.
That's what I immediately thought when.
Yeah, there are a lot of other people thinking of that kind of thing too. I tend to focus.
You know what else? It could actually be like a good plug-in for like the Oculus Quest.
Mm-hmm.
Because you have a video aspect. So
Yeah.
There you go.
Yeah, no, there's a lot of stuff that can be done to make the feedback more engaging. I tend to be more focused on the minimum viable product and the science, and making like one fairly easy to use interface really, really good. And so, programming VR is a lot more work than programming like what I got. So, yeah. But yeah, maybe I could hire somebody to do that kind of thing in the future.
Do you have any of those for sale?
Not currently. I need to finish up the next design and then make a batch. I'm hoping to have that done in.
Around how much would they?
I'm aiming for like a couple $100 for the next batch. I can probably bring it down after that, like in 4 years or something like that, with a better model. But probably about 200 is the
Let me know when they're ready.
the target.
That's a good price, actually.
Yeah.
That's a hell of a good price.
Yeah. I mean, like 2 hours at a San Francisco engineer salary.
Right.
Yeah. Yep.
Oh, yeah, you mentioned that your grandfather helped create HEG.
Yeah.
Can you tell me a little bit more about that?
Yeah, so helped is an understatement. He came up with the idea of using near-infrared spectroscopy for biofeedback. So he was active in the biofeedback community since the 1970s. He married a clinical psychologist, and he was an electrical engineer by training, so he ended up making a lot of instruments that his wife would then use in her clinical practice. And so he went from peripheral biofeedback, like the finger temperature stuff, through EEG in the 70s and 80s, did a lot of EEG stuff. And towards the end of the 80s, he started seeing some papers by this guy, Britton Chance, and these papers were on a new, potentially better and cheaper measurement technique than had been previously shown, called near-infrared spectroscopy. So he decided in the early 90s to build one, finished in 1992, tried to control it, and found pretty much immediately that he could control it consciously. And so he started making them and selling them to his friends. And he built a movement throughout the 1990s and 2000s. He passed in, I think, 2011, though. So I've been working on it pretty much since then. I worked with him for about a year before he passed. And I've been trying to improve the technology and bring it back into the 21st century.